First video of graph theory basics, we will be covering some basic terminologies that we're frequently using in graph theory. This is going to be a little bit long video, so be wary of that because I just want to get through all of the basic terminologies first, and then we can focus on the good stuff later onwards. Also, please know that I wouldn't be using any technical mathematical notations. If you're looking for the correct way to define certain graph theory terms, for example, adjacent can be defined in terms of sets and all that stuff, then this video wouldn't work out for you. But if you just want to have a basic intuition of what these terms means, and if you just want to memorize them in a very clear and easy manner so that you can easily remember them and then use that knowledge somewhere else, then this video will work out for you. So to start off, we will be starting off with what's a vertex. So a vertex is just a dot or a node. So in this case, vertex is just a dot or it's just a node. An edge is basically a line connecting between the two dots or the two vertices. So this line is the edge and these dots are basically the vertices. Then we have what is called as adjacent, and adjacent can be defined into two different contexts. One is with the context of vertices and the other one is with the context of edges. So if we're talking about adjacent vertices, we define them by saying that if we have a line A and we have a line B, then we say that any 2 points or any 2 vertices which are connected and have an edge between them is called adjacent. Now, when I say adjacent, I am strictly saying that, for example, if you have A, B, and C, then you would say that A is adjacent to B, and you can't say that A is adjacent to C. So it should be directly connected to that vertex, and there should be an edge between them. So that's the definition of what's an adjacent vertex. Adjacent edges can be defined as, let's say, if we have a graph of A, B, and C, and we have some common vertex between the two edges, then that would be an adjacent edge. So AB and AC. So the common over here is A. That's why it is adjacent edge. Now we're going to talk about what are neighbors. So neighbors is basically if we have a graph something like this. So we would say that the neighbors of A is defined as, whoops, wrong bracket. It is defined as B and C. So that's just neighbors. Isolated basically means that I think, yeah, I missed one over here. So let's call it 5.5. There's another one called independent as well. So isolated basically means that if I have, let's do independent first. So in independent, if I have this example, this one, A, B, and C. So okay, so if I have A, B, and C, and if I connect them in this manner, then I can say that A is adjacent to B and A is adjacent to C. But you can see that there's no edge connecting between B and C directly. There's no edge between them. So we say that B and C are independent. For isolated, let's take the same graph. So A, B, C, and there's a vertex E. Now vertex E has no connection with this graph with A, B, or C. There's no edge between any of the other vertices of A, B, and C with E. So we say that E is isolated. So in short, vertex is just a dot, edge is basically the line, adjacent basically is a line which is connecting between two vertices. So A is adjacent to B. If there is a common vertex and there are two edges connecting that common vertex, then we say that there is adjacent edges. For neighbors, you just say that every vertex which is connected to some common vertices is called the neighbor. So for the neighbors of A would be B and C. Isolated is any vertex which is not directly connected to any of the other vertices to the graph. Independent is where there's no edge between two vertices, for example, B and C. Now let's move on to what is a simple graph. Now, in a simple graph, there are no multi-edges and no loops. So basically what it means is that this example over here shows that there is multiple edges coming out of A. So this isn't allowed. So this is not a simple graph. If we have a loop on any of the vertex of your graph, then that is also not a simple graph. However, if there is a graph like this, where there are multiple edges coming out of a vertex, but they're getting connected to a different vertex, then that is allowed. So this is a simple graph. The only condition is that it shouldn't have multi edges. So multiple edges is basically when A has multiple edges connecting to the same vertex. That is called as multi edges. Okay, let's move on. Degree, the number of edges a vertex has. So basically in this case, we can say that there's only that B has two edges, which is from B to A and B to C. So the degree of B is 2. C also have two edges, so that's also 2, and A also have two edges, so that's 2. So these two edges, these numbers basically represent the degree of a graph. In this case, A also has 2 because there are two edges coming out of A. There are 3 for B because there's 1, that's 1, that's 2, and that's 3. So the degree of B is 3 and the degree of C is 1. So any edges connected to a vertex is basically the degree. Now then we have an example of an undirected graph, which basically means no direction. So any of the graphs that we have discussed up till now is undirected because there's no direction. And a directed graph is basically means that it has direction. For example, if I have, let's say I take two graphs, so let's take A, B, C. So this is an undirected graph, and the directed version would be something like this. So basically a direction denoting that there is some direction in the graph. Now then we have the degrees for the directed graph. So the degrees mentioned above, this degree was for simple graphs, or sorry, my bad, this was for undirected graphs, and now we're going to talk about the degrees for a directed graph. Since there is direction in the directed graphs, therefore we denote the degree as in degree and out degree. In degree basically means the number of edges coming towards the edge, towards the vertex, any vertex that you're talking about. Over here we're talking about A. And out degree basically just means the number of edges coming out of a vertex. So for example, in this case, the vertex coming out of, the edge coming out of A would be this red line. So the in degree in this graph for A would be 2, and the out degree of A would be 1 in this case. Then we have a handshake theorem, and the handshake theorem basically is the sum. This handshake theorem works for all graphs, so it works for all graphs, all kinds of graphs. May it be simple, may it be undirected, directed, all types of graph will follow a handshaking theorem. But the notation of undirected graphs is a little bit different from the directed one. So the undirected one is that you have a sum from I equals to 0 to all of the vertices that you have in that graph for vertex vi, and that will always equals to the degree of vi, and that will always equals to 2 times the number of edges that you have in that graph. For example, let's say take this graph A, B, C. In this one, we know that there are 3 vertices. So we're going to talk about 3 vertices. Degree of A plus degree of B plus degree of C, which will be equals to 2 times the amount of edges. So the number of edges in this graph is 1, 2, 3. So 2 times 3 would be 6. And the number of degree of A would be 2, because there are 2 edges for A. For C would be 2, and for B it would be 2. So 2 plus 2 plus 2 is in fact 6. So this checks out. So that is the formula for the handshake theorem for undirected graphs. Now for directed graphs, you say that the formula becomes for I equals to 0 till n degree, or you could say the out degree, the out degree of vi equals to e. And similarly, the n degree, let me just bring this a little bit above. And the n degree is also e. So if you take and if we basically sum both of these, we will get this one, which means that basically the directed version is just like it's like a divided version of an undirected graph. Okay, now before I continue, let me just talk about one more concept before continuing. Let's say if I have a loop on a vertex A, this is a very very easy graph, right? There's only just one loop. Now the degree of A is going to be 2. And the reason why this is 2 is because, let's say if I draw the directed version of this, it means that if A has a direction on this loop, then A is basically going to have an out degree. So an out degree, of 1. And it's also going to have an in degree of 1 as well, because if you see, if A is getting out, if there's an edge coming out of A, then there's also another edge which is also coming inside of A. So that's the reason why that A will have an out degree of 1 and an in degree of 1. And if we add those, we get 2. So for an undirected graph, the degree of a loop is always 2, and for a directed version, that's always 1 for each out degree and for each in degree. So I can just keep that there. Okay, then we have an underlying graph. An underlying graph is just the undirected version of a directed graph. So basically, let's say if I take this graph over here, and if you ask me to draw the undirected version of this graph, then that would just be this. So that's the underlying graph of the directed graph of this one. Okay, so we've discussed what is a simple graph. A simple graph is basically having no multiple edges and no loops. So basically it shouldn't have multiple edges going to the same vertex. It shouldn't have a loop, and it's a simple graph. Degree is basically the number of edges connected to connect it between two vertices. Then we have undirected graph, which means it doesn't have any direction. A directed graph basically has direction. Then the degree for directed graphs is denoted by in degree and out degree. Then there is the formula of handshaking theorem, which is the degree of all the vertices would be equals to 2 times the total number of edges in that graph. And the handshaking theorem for directed one would be the out degree plus the in degree would still equals to 2 times the total number of edges. And the underlying graph is basically the undirected version of the directed graph.